पेंडिंग बना रहे हैं वो अगर वो पाती हूँ पोस्ट आउट पे फटाक से डिलीट कर दी कुछ करके रिमूव करता हूँ हम बताने के वाले
Hello, good morning to all of you. Welcome again to all of you. And today we're going to start the next session. But before I wanted to ask all of you that if people can get the to do the simulation, any issue, they can ask me about. We will discuss about this problems that facing to doing the simulations, DFT simulation for about 20 to 25 minutes or something. So if people get try to do the hands-on training via their side, so please without any hesitate they can ask us. Anyone? Maybe some more people are having to join right now. So we'll start it in about 5 to 10 minutes, something. One second. So I cannot download. It's more time to take the download. So Srinivasa sir, maybe from the link you have to take the time to downloading or to accessing the software. It's getting the time. Can you please elaborate to open your device?
Sir, it takes more time to download, sir, because downloading is very slow. Maybe I think the file size is 2.1 GB. It takes time, or my internet issues maybe the problem. I don't know.
Okay.
But I tried several times. It shows error after downloading 60 or 70%. It shows error, so I cannot download your software to the link.
So no problem, sir. You can take your time to taking the download. After The downloading, you can also discuss with me for the any technical issue if you get it. Okay.
Okay.
Another question, if any person have, please. Let me. Is there a Jill Sakai sir available who is currently message on the WhatsApp group to how to perform the DFT calculation when I import the crystal from the CI file? So, Nirmal Kumar sir, can you tell me exactly what problem you are facing? To importing the CIF file and getting the miss some atoms. So could you if you wanted to show us, we can define your problem. So no problem. After that session, we can also discuss. So a person who are telling is how can we perform the DFPT? That is the density functional perturbation theory. So maybe there was the yesterday there was a problem or we are facing to into the some technical issue was there. So we can also do it again. A short. I will be take the short atom or molecule and crystal and try to do the some DFPT calculation. Okay. Okay, I'm going to share my screen and I'll be show you some DFPT calculation once more. I'll take the using the rescue software. And after that, I will perform any DFT any GF calculation, which is implemented for the device property. So I'll be create at that process and at that time I'll be create a device. First, I will take a molecule or crystal and convert into the device. And after that, I'll apply the voltage or something. And after that, you can make the structure into the device. Then you can perform the DFPT and EGF calculation. Same here, I'm also not getting the output files. So you can share your screen, sir. Tirupurai Rao, sir, Gautam, sir. What the problem you are facing? You can ask us this about to. I am giving half hour to all of you to for your queries session.
Hello.
Hello, sir.
Can you hear me, sir?
Yeah, I'm hearing, sir.
I will show my screen. I think structure has some problem.
Okay.
So when I import the structure using zip file, it's not showing a full structure. One layer is missing from both sides of it.
The structure you are taking from online library.
Yeah.
I have.
Yeah, when I use the Vista software, it shows the full structure. But when I import it into Play Studio, one layer is missing from it.
Okay. So maybe if you can show me you can send me some WhatsApp image or you can share it. If you are on your desktop, no, you can share your screen and show me that what.
Can you see?
Yeah, I'm seeing. Is that the structure? Is that the structure? But
Yeah, yeah, there is
okay,
a blue atom side. That has been in both sides, but the two sides are the same.
okay. So what atoms you are missing there?
Zirconium.
Maybe you taken from the like material studio, right?
Yeah,
With this
no, no,
system.
no. I imported from Open Discover to
Okay,
database.
material projects. Okay,
Yeah,
yeah, understood. So actually, you're a complex. You are taking the complex material. So after, no problem, we'll take this into the queries, and after that, we discuss about more about what exactly problem you are facing. Okay.
okay.
So, okay, see, I have not. Okay, sir. Yes, sir. Gautam, sir.
Can I share my slide
Yeah, please.
desktop
Yeah.
screen? So is this visible?
Yeah, you are visible, sir.
No. The device studio
No,
interface,
you
is
are
it visible?
not. Your meet dashboard is showing.
Okay, wait. Now is it visible?
No, still not. Yeah, you are visible now.
Just
Okay.
a second.
Okay. Yes, sir. Sir, if you're not able to show your exact problem, so after that, after the session, we can discuss on that particular question. Okay. So, okay, we should getting to start this session. Okay. So maybe participants are coming, all maybe the person who are coming. Let us start the session. Okay. So can you, sir, can you, I'm going to present my screen and you can remove your presentation right now. So stop your presentation.
Yeah, I have stopped it. Sorry for the delay.
No, sir, no problem. After that, we'll discuss, no problem. Because we have also a limited time now. So I think am I visible, no? Yeah. So first I have to open the device studio and I'll be do some. So actually, the person first asking for the DFPT calculation. After that, I will perform the any GF, DFT, any GF calculation. Okay. So as we are doing, first we take the crystal of it, we create this structure, and after we did the DFT calculation using the Nanodcal software. Okay. Now after we perform the this this crystal and we perform the DFT calculation. Okay. So you can see, I will perform, I will copy this. You can copy the material as well. You can take the 01 something. Okay. Now this is your material. This is your crystal. So for doing the DFPT calculation, you have to go on simulator and there's a rescue, as you know. For rescue, there is a DFPT. For DFPT perturbation theory is there. And you can select your type of SCF method and you can what type of things you have to calculate it, like optical properties, Raman properties, phonon band structure, and phonon density of state. You can take both of as well. And after that, let the parameter is be same. You can select the GG, PB, and you can control the iteration control. You can take the values of iteration control. You choose the basic set. You can perform the spin type, or you can go with the phonon band values. And if you wanted to change the abelian zone path, you can take from here for x-axis. And for phonon density of state, you can change your values as well. After that, you have to do the generate files. And last, we have to only do the SCF input. First, we have to run the SCF input and run it. Okay, so let me save it. So your SCF input and SCF input calculation is getting started. And for dielectric input, you have to run it. This is all the things are for basically for DFPT calculation. In the DFPT calculation, you can calculate the phonon input and run it. Phonon band structure, phonon density of state. You have to run it, all of them. You can see all the calculations are getting started. Yes. Now, if someone wanted to do with the hands-on, they can do with their own side.
Excuse me.
Yeah.
Once the job status is done, so do we have to save it or just to close it? Because
No, you can
yesterday
close it.
also I same
No
the
problem. When the job is done, no, you don't have to close the device studio until the
no
calculation is
no.
completed. Yeah.
I am talking about the file like here in on your screen crystal one something and
This
it
file,
was done.
this file, this file.
Yes.
So no problem. You can
Yeah.
directly cut it. No problem. It's close it. The calculation will be running in the background until the device
So
studio
once
or
the calculation is over, after that,
yeah. When the calculation is over, you can also close it. Hello.
so later on where we have to see that if we want to see
That
again
that file.
file.
Okay. So let me show you. You can see here. When you go any file, you have to simply right click and you have to click open containing folder. Okay. So when you click the open containing folder, it will be take you into that file directory where you are doing all the job. You can see here, all the calculations are happening here in this rescue DFPT. That is your D drive. I'll save it the webinar, demo, crystal name, and rescue DFPT. And after this, in this, all the input file are there. For result part, you can go into the result, and after the completion of this simulation, you can get the data into the result. Okay.
Okay, got it.
Okay. So in the meantime, let the calculation happen. Someone asked will perform a graphene structure, try to create a nanoribbon of graphene. So you must take to making the graphene ribbon. So you can go with there is a tool build, and you can see there's a tool called graphene nanoribbon. You can see, and in which you can put you can take the element according to your convenience, and after that you can put their crawl vectors. Like I will be put it here. So let the values be default. You can click preview. You can see this is a small nano ribbon of carbon. If you want to change the atoms, you can also take from the here. And I will not take. I will be taking to the default. So it will be click and it will be shown like that. After that, you have to click on build. You can see. Now you have to go, there is a build, and the build, you have to create some vacuum and expand this material, this molecule. So there is a redefined crystal. So when you click the redefined crystal, you have to put, I will be expand into the Z direction. So I'll be take this value and click preview. Okay. Am I audible? I think someone is muted my mic. So my am I audible?
Yes.
Okay. Okay, sir. So you can see this is the short graphene nanoribbon. After that, you can click preview and click build option. So now this is the graphene nanoribbon. We want it to see into the different view. You can click on XY view, XZ view, and YZ view, or you can see into the YX view, or you can see into the ZX view. Okay. So now this is the simple graphene structure, molecular structure. You can do the center as well. And after that, now I will be try to create this graphene nanoribbon into the device. So to making this graphene nanoribbon into the device, you have to do simulator, build option, and there is a tool called convert to device. You have to click on convert to device, and you can see to converting to device, there is a electrodes are given for left, right, bottom electrode, top, front, back are given. If you click on back or front, okay, you can also click with left and right. You can see when I click left and right, there is some default values are taken into the Z direction, and you can click on preview. When you click on preview, you can see there's a -2 at the Z, the both direction, left and right. There's a 2.4595 of angstrom thickness of electrode is generated in the both side. Now this is your device, graphene nano device. After that, you have to click on build. Now you can see this is your build option, and calculations are happening. You can see the FPT is having to completing the equation. So you can also see into the different view of this device. So this is your graphene nano device. So now for doing the NEGF calculation for DFT NEGF calculation for this graphene nano ribbon device, so you have to go with the simulator, and there's a Nanodcal. Now when we last time the calculation is done here. You can see when we are taking the crystal molecular structure and we'll go to the simulator and Nanodcal, some transistor, IV curve, all things are not open here. But when you choose the device, when we are making this device, we had making this device, and we are try to solve this, try to do the DFT NEGF calculation for this nanoribbon and go to the Nanodcal. This transistor, IV curve, analysis, transistor, it's these are the open. Okay, so you have to go the SCF calculation. You can see when you click the SCF calculation, and it's already shown SCF calculation for device. Okay. So in which, yeah, yeah, someone asking some question. Is there a problem? Am I, okay, I think my screen is not visible. My screen is visible. I think, hello, Gautam, sir.
Yeah, your screen is visible, but it's very like video is very pausing and then going. So I'm not able to get how you have come to whatever you have done. I didn't get
Actually, sir,
it at all.
your maybe internet
It is
connection is
visible.
slow.
It is.
Internet connection
Yeah,
is slow.
there may
But
be some connection problem.
yeah, but I will recording this video as well. We will provide it to you after the session. Okay, sir. If this
Okay,
time you
fine.
are if this time your device if network is working properly, we can I can make again to this structure. Or you can if I wanted to get ahead for doing this simulation. Okay, no problem.
Okay,
Let
fine.
me. Okay. So now this is your device, Graphene Nanoribbon device is created now. So you can see the SCF calculation for device. Here the any
In the device, so in the device, how to find whether it is the contact pad of transistors of gold or some other material. Is there any effect on property?
are you saying something? I'm not getting you.
I'm asking is the device characteristic. Um, what is the device characteristic which element has it taken for the device? Like we are making transistor, so the contact pad material, graphene the channel material, and what is the contact pads, and what is the gate.
Sir, you can mute your voice. Actually, we are not getting you. Let me complete this session. Okay, after that we'll reach you, and or you can also reach us. Then we'll discuss about your particular question. Okay, sir.
Okay.
So you can see our SCF calculation for device. This is your basic SCF parameter. You have to put it to take your to get your SCF input. So here you can choose your basic settings value, in which you can give the electron temperature value, electron energy cutoff, exchange correlation. You can take either LDA, GGA, or something. We'll take the GGA. And in the contour integral, you can put the values like their lower bounding value and the Hatry or electron volt or whatever. The whatever your convenience are there for to doing this to calculating the result. There is a you can see there is an electrode is also generated into the SCF calculation. You can see in which you can also give the electrode voltage and K point and electron temperature. Let the all values default, and after that you can do the iteration control. Into the iteration there is a density matrix, Hamiltonian matrix, and if you wanted to give some energy to this device, you can choose the total energy, and after that you will go with the this basic set, and you can go with the Hubbard terms as well. You can take this LDA plus U, and that is your Hubbard term. You can also do the Spintronics application for the device as well. Let me show you. Let the default. After that, I will be perform a one spin type calculation for the material or device. Okay. So when you click on generate files, you can see when I click the generate file, there is a three file is created: device, left electrode, and right electrode. And what folders are there in folder? What files are there? You can see all these are the input files. for the device, for left electrode and for right electrode. When you open this scf.input file, right click, open this. You can see when you open this, this is the input script file for the left electrode. You can see all the things, how many atoms are there in the left electrode. There is 8 atoms. And what basic sets are used, that is the PB, PZP, and your electron temperature, and the energy cutoff, what type of exchange correlation you take, their key point sampling values, and we choose no spin. So now, as at the same method, you can go with the right electrode. Since the left and right electrode are the same, so the input file will be the same. Okay. Now you can go with the device and you can click open with, and you can see this is the device SCF input file in which their calculation name SCF, their basic settings value, their energy cutoff, their exchange correlation type, their key point sampling values, and there is a description of electrode. In that description, we had taken the system dot number of leads. There are 2 leads. Leads stand for your electrodes. This is the first electrode. So you can see there's a nanodical object.mat file is there. This nanodical object mat file is when you calculate this left electrode. So whenever you have completing any SCF calculation, after that there will be a mat file will be generated for the particular SCF input file. Left electrode, this file will be generated, and this file will be taken by the center part of the device, which is our device part. And for the right electrode, this will be the same thing. This is your contour integral, in which you have chosen the 1.583 for the lowest energy point, and your number of points for the complex encounter. And after that, you guys also choose the no spin type, and you did not choose any energy. So this is the you can see this is the row matrix 1 exponential 0 minus 0.4 10 to the power minus 4. This is a Hamiltonian matrix. You did not give any total energy. So this is the inputted, this box. And after that, you can see all things are how many atoms are there into the center part. So there is a 104 atom. So after that, this is the input file. So now okay. So now to simulating the device part, you have to first simulate the electrode. So you have to come with the left electrode, right click and run. And run it. And again, you have to go with the right electrode, click right and run. So now after that, you have to go with the device part and click right and click run. You can see there is a things where DFT calculations are happening. After that, one calculation are completed. The next will be our electrodes and device will be getting started to the simulation. So in the meantime, you can select another analysis using the Nanodcal. You can go with the Nanodcal, or you can see the analysis. In the analysis, you can choose the calculation for the device, for the left electrode, for the right electrode as well. So when you click the left electrode, so it is a material property which will be taken. You want it to go with the right electrode, it will be take the material properties. But when you choose the device part, so it takes the whole device properties. Okay. So you can see in the device part, you can calculate their density of state, effective potential, total energy, scattering state, transmission, photocurrent, IV curve, charge, electron density, conductance, thermal. This conductance is the basically DC conductance, and thermoelectric conductance, Seebeck coefficient, and AC conductance as well. So we can choose the density of state, total energy, transmission. You can go with the IV curve or electron density, conductance, Seebeck, AC, whatever you wanted to calculate. So when you go with the density of state, there's a K point sampling value you can put by yourself. If you wanted to that is or you wanted to do the PLDOS, projected density of state or local density of state, so you can select from here. You can go select the atom. When you select the atom and click this LDOS, so this calculation will be happening for PLDOS. Or if you wanted to simply do the LDOS, or so it will be here you have to select. After that, you have to put the values of like localized position, region position, and region grid numbers. These values you have to put by yourself. And if you did not select anything, so this calculation is only happening for the density of a state. Okay. So you can go with the total energy as well. It will be not, you have to know with any parameter. So you can also go with the transmission. So in the transmission, you can select their K point sampling, their number of energy points, their energy ranges. Like we can select the energy range from -4 to 4 or something. Will be a good, or let be default value taken. Like here we are given -10 to 10. So you can also go with the IV curve. This IV curve is completely coming for a single point. For the multiple values, you have to take the different values. For IV curve, we have a separated videos on YouTube. You can go with that videos. And if you need any particular information about IV curve, and so I will provide it to you. So this is the electron density. You wanted to calculate like charge, total electrons, rho, bond, redistributed, d rho, del rho. This is the your I think neutral atom, RNA, RHONA. So you have to select the charge. You can go with the conductance. You have to put it the number of energy points and their K point sampling. And you can go with the Seebeck. In Seebeck, you can put their energy ranges, their temperature ranges, and you took the interval as well. And the AC conductance, there's a AC conductance value you have to put in by yourself, like their frequency, maximum frequency, and number of frequency points. Like you have to select this 500. And you can took the temperature. You have put the K point sampling and the energy point, their energy intervals. This all parameter by putting by yourself to doing the simulation. Like we also select the photo current. Someone wanted to calculate the photo current. So for the photo current, there's the polarized basis. The linear vector, polarization vector are there. So which type of things polarization we wanted to like linear polarization, left circular polarization, right circular polarization, electrical polarization, oblique electrical polarization. Like let the default value, or you can select their theta value, and you took the and you can give the interval as well. Like we can select the 180 degree and I will be take the interval of 30 or 30, and you can give the energy points for the photon, uh, and after that you put the interval, and you can give the key point sampling value, and after that you have to edit the irritated atom. So you have to select all the atoms, or if you wanted to give some specific range of atoms, so you can also select, like I selected, and give select and click OK. And when I click generate file, okay, you can see when I click the generate file, all the input files are coming for the device, like their density of state, total energy, transmission, IV curve, electron density, conductance, Seebeck, AC, photon current, photocurrent. Okay, now the next thing we have to run all the simulation. So you have to first, since we have already run the FCF.input file for the device. So after that, we have to run the density of state, total energy, I'll be transmission input, IV curve, we can perform the electron density, conductance, Seebeck, to calculate the AC, and photocurrent as well. Now you can see the all calculations are getting in the queue form. After this will be one by one. When you get to completed, then another will be started. So by that method, you can calculate, you can create your structure, and after structure, you can convert the structure into the device. And after that, making the device, you can perform the SCF calculation for device and electrode. And after that, you can you can do the analysis of the particular, this type of uh, parameters. Okay, so now you can see currently our rescue DFPT phonon.input is running here. So let the let the calculation is happening. So either someone wanted to do the hands-on by their side, they can also do, or if you get into problem to making this structure, they can ask us until we are doing the calculation. You can also create nanotubes as well.
Can you once again show how you have bring about this graphene here?
Okay, let me show you. Okay, let me create the from the scratch. Okay, okay. So okay. Basically, this is the structure, but we are going with the scratch. So there is a build tools. Into the build tool, you can see there is a Graphene Nanoribbon. GR Nanoribbon is there. You have to click on this tool, and when you click on this tool, there is a dashboard is shown like this. You can give the structure type and crawl vectors values. And if you wanted to take some standard specific type of material, you can take from like this. Okay. So we'll let it be default value. We choose both of them, the carbon and structure type and RM. Their crawl vectors are 2 by 2, and click preview. When you click the preview, you can see this is the simple nanoribbon structure, and you have to build it. Now this is the graphene nanoribbon. So now you have to expand into the some specific direction. So you have to come on build option, and go to the redefined crystal. This is basically for the making the vacuum and expanding the uh, atoms into the X, Y, Z direction. For the molecular, for the device part, you have to buffer option. I'll be do the some buffer as well in the another session. So you can see I'll be put some values. Let me take this value into the Z direction. I'll be take the 15 and you can click preview. When I click the preview, you can see this is the graphene structure is ready now. So if you having some some specific thing, you can also expand into the X or Y direction. So I'll be take like 3 here. So I'll click preview. You can see it comes into the X direction, 3 of them. Want it into the B direction. B means Z direction of. You can also take like I'll take the 3 as well and click preview. You can see now this is the graphene ribbon structure. Different. You can also expand more of them. So let it be 1 as well, 1. And click preview. And we'll go with this structure and click on build. You can see when you click the build, your structure is ready. You have to click on right and you can, this is a tool, 3D view rotation mode. You have to click on here and on the double click, you can see, you can move the atoms like this. Or you want it to see into some specific type of orientation, you have to click on this, the 3D viewer, and you can see into the X direction, XY direction, YXZ direction, YZ, and YX, and ZX as well. Okay, you can, if you wanted to, like there is some redundant atoms are going out of the vacuum. So you can do, there is a tool center, you can click on center, the atom will be shifted into the center part. Okay. Or someone wanted to change the atoms. So change the specific atom, like they are wanted to some doping. So you can select some particular atom, like here wanted to some doping. So you can select the atoms like this. And there's a tool called replace atom. You have to click it here. And when you click here, there's a periodic table is open. Now I wanted to take the oxygen. Okay. So I'll click on O and click OK. So you can see now our bond is changed, our material atom are changed, and as well as in the properties window, you can see their chemical formula is also changed. That is a C104O14, and you can say by this you can do the doping as well. Okay. Or someone wanted to do the another thing like someone wanted to do the hydrogen passivation into this structure. You have to do select all atoms, and there is a, you can see there's a hydrogen passivation. So simply they have to click here. So when they have to click that position where they want where the molecule can take the hydrogen passivation, it's take as well like this. Okay. They can also use the hydrogen passivation. Someone wanted to see the distance angle between the atom. They can also perform the things like that. I'll show you. Like we wanted to see the distance between 2 atoms. So you have to select 2 atoms with control. So 1 atom and the second atom is selected here. Now there is a tool which is there is a tool vector between 2 atoms. They have to click here, and you can see and do it again. Select the atom, first atom and second atom. You can see when I select this, I'll get the value of between the 2 atoms. That is about 0.7 to this is the distance between these 2 atoms. Or you wanted to see the angle between 2 atoms, you have to click here, angle, and select the atoms like this. and I'll select the three atoms, and you can see the angle between these three atoms are 120 degrees. Okay, these values come for the angstrom, which we are calculated the, which we are taking the distance between two atoms. Okay, so these are the basic tools you can use. You can by using these tools you can perform the enhance your material properties and the things. So you can see our DFT calculation are still happening. So can take some time because there are a number of atoms are there. So in the meantime, I will be perform some another thing. I can show the another application of this software. Regarding this structure and calculation, if someone have any particular question, they can please ask us. Ask me.
Hello, am I audible?
Yes. Yeah, sir. Yeah.
Sir, as you mentioned, this DFT calculation of the known file.
Okay.
Suppose we have some experimental data,
Okay.
right? Suppose some kind of a metal oxide we have designed experimentally, and fundamentally we perform XRD. Now, on the basis of that XRD data, how we can generate the file in this Nanodcal to calculate DFT and all things.
If you have material, CIF file of the material, particular material, no?
Yeah.
So you can perform the calculation. You can took the import option. You can see there's the import option is there. You can import the, like I wanted to show you, like when I click the import option, this like these files are into having the CIF file. Basically, this CIF file having the crystal information of the particular.
Hello, I have one
Yeah.
question. So is this software is flexible with large system kind system is containing about 96 atoms or more than that?
So your voice is not coming.
Okay. Am I audible?
Yes, now you're audible.
Okay. Thank you. So I had also a project. After that, I'll be show you the transistor and the NGF calculation I done the earlier. So I wanted to show them some another ability of this calculation. Let me show the that person he has asked.
Hello.
Yeah.
I asked one question. So is this software is flexible with large system containing system contains 96 atoms or more than that?
Yeah,
So
yeah,
that
it is it have the ability up to solve the 20,000 atoms if you have
okay.
particular type of HPC. Okay. So you can go with the up to 20,000 atoms to perform the DFT and DFPT and NHGS calculation.
Okay. Thank you.
Yeah. Okay, thank you. Let me show you. Uh, some people wanted to, let me show you some doping. There is another tool is simulator. And we see this is the virtual crystal approximation type of things in which you can perform the doping. Okay. Now someone wanted to create PN junction or something. So for them to creating the intrinsic or extrinsic type of material, so they can perform the simulation using this VCA. Okay. So for the VCA, using the VCA, like will try to perform the VCA for this nanoribbon. So you can see. So like you have to do the VCA part. For VCA type calculation, I will show you some for the semiconductor. Uh, First, I'll be take the silicon atom. So file, import, and import local name. There's a in the 3D materials in the semiconductor, you can take the silicon, like silicon we take. Now this is the silicon. We can go with this silicon and go to the simulator and Nanodcal. And you can see this is a VCA, that is the virtual crystal approximation. This is used for the mixture vacancy and to do the mixture vacancy and mixture atom. And you can see after that, you can select their LDA type, basis type. Like you wanted to, which type of doping you wanted to do. Like first you have to create the doping type. So it is a P type doping or N type doping. This value will become to default. When you click the P type, it will be take 0.99. And when you click the N type, it will be take 1.001. And we'll select the P type and click generate files. Okay, you can see here, when I click the, there is a folder is created and in the silicon and there is the VCA dot input file is generated. And for this P type, there is a mat file is generated. So first we have to calculate this VCA dot input file. So I'll click the VCA dot input and we have to run it. And you can see, let this calculation to stop here because it will be take some time. And that's why I cannot show you the complete things. But by your side, you can perform this like we are doing for the graphene nanoribbon calculation. They can perform by themselves. So for stopping this calculation, you have to let the first FPT is calculated. So after that, we will stop the calculation for this device part. Okay. So now you can see I run it the VCA.input file. So the person or not. Okay. So It is still getting running. So we can stop this calculation. Okay. Maybe I have to stop this calculation right now. It takes time. Okay, DFT calculation not take time for because we have taken a lot of numbers of atoms now. So that time we need to come to have complete the simulation. It may be taking time. So we'll go to the another part. I'll be stopping this all calculation. After that, we'll go with the VC. And I had done already some project as well for the device and DFPT, and I'll be showing you what the results. Okay, so I'll have to stop this calculation. I'll be device close this structure. I'll run it again. Now the all calculations are, you can see, stop here. So I was showing you the VC calculation. Okay, so for the VC calculation, I'll have to run it this VC.input file. So you can see I run it this VC.input file. This is basically run for this and p-type doping. Okay, so this will give you the you can go with the extrinsic type of material. So now, okay. So now your VC input is calculated here. When you click on right click and open containing folder, you can see your calculation is still completed or not. You can see there is a silicon slash VC slash silicon 0.999 PA, that is maybe a vacuum atom. 0.001 is created. This is a mat file. This mat file is takes the complete information about your structure. Okay, so let me show you. Now we have to do the p-type. We done a p-type. Now we go with the n-type doping. So for the n-type doping, you have to go with the simulator, Nanodcal, and do the VCA. And here you can, if there is a lot of elements are there, you can also select by yourself. And we go to the n-type doping. And when I click the n-type, the value gets changed, 1.001. And it is a default value. If you have some specific value, you can change by yourself. Okay, so you click on generate files. So, okay, so you can see when I click the generate file, another VCA input file is generated. Now, after when this input file is generated for the n-type, you can see if you wanted to see the input, you have to simply click on open with. You can see this is the for the VCA pure atom basis here for 1.001. Okay, this is basically for the p-type doping input. So you have to run it again. Okay, you have to run it again. Okay, so you can go with the open containing folder, and you can see your another n-type of doping concentration mat file is generated. Now we'll do some analysis of this mat file into the MATLAB. So let me go into the MATLAB. Okay. So in the DFPT calculation, the meantime, the people who are asking for the DFPT calculation, they can perform the calculation like as well, but we did not get the complete simulation. So after that, they can do the simulation, and if he he or she getting the issues for getting the results, then they can ask me for to WhatsApp or something. Okay. So now your MATLAB is open. It will be open. Someone who wanted to work on the indium arsenide model of indium gallium arsenide model type structure, they can also perform the using this VCA tool. If someone wanted to model the indium arsenide model of, it can be used the mixture atom type of calculation using this VCA. Okay. Okay. Now this is, MATLAB is open. Now we have to take this MATLAB into we have to take this file into the MATLAB. So it's already into the yeah. So we are doing this silicon. Okay. So we'll open this silicon one, and you can see. Now you can see silicon VCA and both files are generated here. And you can go with, I'll show you. Okay. So we have to load this information to the MATLAB. So first we'll go with the P type and load this silicon VCA input. And you can write data dot atom. We are doing for the P and atom for both for N and P type will be the same input. So you can see 3.9960. This is the concentration of the your doping concentration of 1000. If you calculated it, if you wanted to calculate, you take the this is the doping concentration. So it will be going to the about to 3.996% of doping concentration. So you can also load this mat file and type data dot atom dot, and you can see this will become 4.004, and this is the concentration of the silicon atom into the 1000 atoms. So you wanted to see, you can calculate. If you wanted to see the percentage of this atom, you can multiply by 1000 or 1000. You will get the percentage of your percentage concentration of your material. No, you have to like you take the 0.99. So for this silicon atom, you have to for p-type doping, you have to multiply with this 3.9960 into the 0.99 to see the concentration of atom into the 1000 for the 1000. For this n-type doping, you have to write this 4.0040 into the multiply by 1.001. That will be give the percentage concentration of the n-type material into the into the 1000. So it is the basic calculations are there. So they can perform this. Okay. So now after that, you can see now. So another thing I wanted to show you another calculation. So now some people are working on the transistor something. Okay. So some people are who are working on the transistor or wanted to make the crystal. After that, they have make the structure. So you can see, go to the file directory and import local, and into the they can come with this device studio example, and we have a already example which is a RM organotile AU. This is the structure. Either you wanted to make this structure, you can create by yourself as well. So it's no problem. Now, like someone wanted to do the simulation of this crystal, they can also perform by their own self. So, like, give me a second. Some people ask for the MOS2 type of structure and some this type of structure. So basically for the MOS2, if someone wanted to create MOS2 type structure or armchair structure, so I try to make the structure. So you can take the material from the online library, or there's a offline library as well. You can simply go to the import online, and you can click on you can MOS2. Like if you wanted to create this type of structure using the device, we'll take this one, MOS2, and this type of space group. You can click on add. You can see two type materials are coming to this having a chemical formula MOS2 S4. So we have to remove this one atom. So I removed it. And now this is your MOS2. Now you can do the into the center as well. Now if you wanted to make the structure into the center, you can simply click in the from your center. And after that, now I have to build this. So for the building into the device, so you can go with this build and redefine crystal. And to the redefined crystal, you have to put some values, like I'll be put it here, -1, and I'll be take 12, or you can take the 11, you can take 11 as well, and let it be value default, and click preview. Okay. So do it again. Build option, redefine crystal, and I'll put the value -1. And you can put the value 112, or according to you, convenience. I just wanted to create a structure preview. You can see this is the simple MOS2 material having the material having the some vacuum into the structure. So you can click on build. So you can, when you click the build option, you can see it change the chemical formula is getting changed, MO24 and H48. The lattice parameter is also changed, and the number of atom is changed. So now after that, you can select the orientation. Now we wanted to, if you wanted to change the coordinates, or you wanted to change their type of material, this is basically armchair direction. You can see this is the armchair direction. And you wanted to go with the zigzag, you can also go with the zigzag as well. So we'll go with this structure to making the structure. So this is also a type of structure. Now after that, you have to go with build and convert to device option. You can see when I click the convert to device option, and I will be select the bottom and the top electrode. You can see when I click the bottom and top electrode, it's the value getting changed. And you can also change by your convenience. Like I will just put this value -6. 0.564. Basically, this value will be x and y direction. So one value will be plus direction and second will be the minus. So you can click preview. You can see now your device is ready now. You can click on build option. And after that, you can perform the SCF calculation simply using the Nanodcal MEGF calculation simulator and Nanodcal and do the SCF calculation. For the SCF calculation, they have to put the values according to their convenient, what type of things they wanted to calculate. So these are all the things dependent upon their particular research. So these are the basic setting as well. I explained you earlier. So pin type. You can see basic sets. I will take this value. Someone wanted to do the hands-on, they can also do the same. And this is the value. They can also perform the calculation on their own desktop. So I'll be putting this value K point. And this will be 12 and it will be 1. I will take the LGA, exchange correlation, GGA, PV96. And after that, I'll be put the contour integrals value. You wanted to take it. Now, electrode value, they can give the electrodes voltage as well from here. And the expression control, their basic sets value, and their spin type calculation. All type of things they can perform. And simply click on generate files. As I shown previous, their device SCF input, bottom SCF input, and top electrode SCF input is generated here. They can do the calculation like this: SCF input run, and this run, and run this device as well. So now one thing actually I did not recognize you into the VCA. Now after that, when this type of calculation are have completed now, so you can select this when you making the device. You can see like this is the device and go to the simulator option, Nanodcal SCF calculation. You wanted to do the doping into this structure, so you can see into the basic set. There is a spin, there is a doping. You can see, you can select the doping type. Like you had created the VCA input, and after that you can use this VCA input. You have to select this VCA input here, this VCA values, and you have to click on search and select the region you wanted to do the doping, and select that region, particular region. After that, select and do the OK. Then after they will be get the that particular region with particular type of doping. So here into the SCF input, SCF calculation, they can do the doping. So for MATLAB is using for the two values part. No? So if you wanted to take your output values into the raw data, so MATLAB is an essential tool for basically this software is written to the MATLAB as well. You can, as you know, when we are doing the calculation, this is a particular all the things after the calculation we get the SCF, we get the .mat file as well. So seeing the result into the mat file, we'll have to extract the mat file. If you have another software which supported the mat file, you can also do the calculation from there. But I did not have the knowledge about that. There's a mat file. You did not need any lot of things for doing the MATLAB. These are the basic essential things you can perform into the MATLAB. Have just load the data and type the data, and after that it will be gives you a complete information about your structure and devices. Okay. So here you can select the doping type. So here we are not take the doping, and you can do the spin type. So this is basically the part of doping, and you can see you run the calculation as well. Now after that, you can perform the transmission calculation. Like we wanted to calculate the transmission, so we have to go with this analysis and go into the transmission and wanted to do the IV characteristic. Here for IV characteristic, I wanted to show you the thing. Okay, you can take this input. You can click on generate file, and like you have to select the transmission input. So for this, you can run it again. Will not do it the IV current curve as right now. So let the calculation is completed. Maybe after we'll discuss the output. Let me show some another file. I if someone wanted to work on the work function or something, no, they can also perform the work function calculation. Work function, formation and absorption energies. Many more properties they can calculate. Like we had that wanted to open this file. To show you that I had this is the this was the project which I did not get the complete simulation. So I wanted to show you. This is the previous structure which I completed by myself, in which I calculated the lot of things. Let me show you. You can see I calculate density of state. You can see this is the density of state of this graphene nanoribbon structure. So this is the density of state structure. So this is the number of state versus energy graph. If someone wanted to change some, see the result into some specific, then they can do via this their own site. I wanted to see into the from the -1 to -2 to 2. And apply here, and you can see the result like this. can also do like for the on the Z axis as well. It does not to go with on that. Now this is your density of state for this graphene nanoribbon device. Okay. So I had also some projects. Let me show you. If someone wanted to work, someone are working on some specific type of calculation, they can ask us as well. This is the nanotube. You can see this is the nanotube structure which I had created. If someone wanted to know how to make the nanotube, they can. We can also perform the calculation. We can also make the nanotube. And after that, I calculated the transmission input thermoelectric current and see that. So now this is your nanotube structure. And in this structure, I calculated the so you can see this project is also available on the YouTube, in which I make this structure, this molecular of nanotube molecular structure, in which I created a stone wall defect. Or as you can see, I created the stone wall defect here. And after that, I performed the calculation like band structure of this nanotube. Let it be open. You can see it's a value, a complex value of it. If you wanted to see the result into some specific ranges, you can do via this your side. Like here we select this values from -1 to 1. So you can see this is your value. So you can also see the result between some specific ranges like this. 0.5 you can select. So this is the band structure of this nanotube, nanotube. And, so you can do the calculation. And after that, I calculated the eigenstate of this. So now this is the eigenstate of this nanotube. Okay. So in which you can do the, you can feed into the 3D, 2D view as well. This is a 2D view of this graphene nanotube. And you can also feed into the 1D graph. So or we wanted to see into some specific ranges, like we did it for the tank. So can take on 20 as well. That's 40. So now this is the eigenstate value of. So now that method, you can make your structures, you can build your structure, you can perform your calculations after that. You can do the DFT calculation, you can do the DFPT, any GF calculation, you can do the DFT implementation using Rescu software. And after that, you can perform your calculation like this, and you can visualize your graph. You can extract your data from the MATLAB. So these are the things, are basic things are you can use using this device studio user interface and using this simulation engine. Okay. So there are a lot of things are there. When we had provided a 2 month of license, you can perform the calculations. You can do the simulations, and if according to your research paper or interest area, and perform the things. After that, if you get any type of issue you wanted to resolve with us, you can also contact with us. So now, we had a lot of applications are there. So you can see this is still are running. So I wanted to show you. I will create a device by my side and try to doping into them, particular doping into that particular structure, and try to calculate some photo current and IV curve and lot of things into that particular material, particular device. So if someone tried to make this structure and perform the calculation, if having any issue, they can ask me until the calculation are happening. Anyone? You can also calculate the phonon thermoelectric properties. Okay, so thermoelectric transfer property, you can also calculate for the materials part. So let me show you project practical by my side. So I'll be take an atom. Let me show you. So I will take the silicon atom. So I'll take the silicon, like we had taken already a silicon. So we can copy this. And after the copying, you have to go in the simulator and the build option and click on the define. I'll be take value like this. So now this is your silicon molecular of cubic molecular silicon cubic molecule. You can build it, and now we'll be doing some transport calculation for this material. So let me show you. You can also calculate the Hessian matrix. So And this will calculate the phonon band structure and something. So let me show you. Now after that, you have to go with the Nanodcal and do the SCF calculation. And this in this SCF calculation, we have to put the values like exchange correlation will take the GGA type, and for the key point sampling, we'll take the values 1, 5, and 5 as well. You can also perform with me because this is a hands-on planning, so they can also perform with us. So that can be he or she get the better understanding of that software. So you have put this input file, and you can select the iteration control values. Value will be 5 as well. And if you want to change, take the value to the electron volt or ribbon, they can also change. Station, basic set, and spin type. Now after that, you have to click on generate files. Now for this material, your Nanodcal SCF input is ready. Now you have to run it. Since this calculation is getting started, and after that, we have to go on simulator. Let me close this for 6 seconds. You can see our calculation is still running for this bottom electrode, so it will be take time. So by your side, you can perform. You have a lot of time, and we have the 2 months of license, so you can perform by yourself for that MOS2 material if they are interested. So I'm closing this that particular structure. I'll open it again. Okay, so this was the same project was open. And now this was the practice project. So for this crystal, we'll do some Hessian matrix and phonon band calculation. So for the Hessian matrix, you can go with like this. You have to run this SCF input. We put it all the input files. You can also see using OpenBit. So you can run it, and you can see into the job manager. You can see your input file is getting started. Then after, you have to come with simulator options, Nanodcal analysis, and we will take the Hessian matrix, Hessian, and the Hessian, let the values will be default, and you have to click on generate files. So your Hessian input is ready now. So you can run it. So you can also perform with me. So we wanted to see the input file. So you can see this is the input file for the Hessian, in which whatever your input are put it here into that Nanodcal analysis dashboard. So all the things are written to the SCF file. So when this calculation are completed, so you can see your whatever your calculation are happening, there will be a log.txt file. You can also see the status of your calculation into the log.txt file. You can see calculation is running there. You take the exchange correlation, this, and your total number of atoms and some cell atom or no spin, periodic 3D type atoms. So these all things are shown here like this. Let it will be not take the lot time. Yes, when this Hessian input when the Hessian input is calculated, then you have to do the phonon band calculations using the Nanodcal. So you have to go on Nanodcal and analysis and do the phonon band structure. Select the phonon band structure, and you can also generate files for this, and you can run it. After that, you will get the output of your data. So let me show you. It will take time. So if someone have some particular question, they can also ask me, So maybe in the meantime. So making the interface structure. So let me show you an interface structure. How could you make the interface structure? Okay. So for that particular type of material, like this is your, this was your MOS2, and we'll take the MOS2. This is the MOS2, and also you can take the. I just try to take the structure and with this graphene. Okay, so you can do with two. We have a some tool build, and there's a tool for interface builder. Now this is your interface builder structure, where you can select the atoms. Like I wanted to do with this 2/2 Graphene nanoribbon redefine. So I'll be selected it into the structure A. Into structure B, I will be select this MOS2 redefine. So I selected the MOS2, and after you have to do the match. You can see I click the match, and it matches it. Sometime for the angle and orientation reason, there will be not give some error for the angle. Okay, so you can click preview. You can see this is your structure we are getting here. So you can see this is the graphene. This is your interface structure we are creating. Actually, there is some van der Waals force work here. So maybe this not get interact with the complete. So by using this interface, builder interface, you can not able to create an interface in one graphene. You can see here, you can also do like this also, like you can take this graphene, that was the nanoribbon. You can take the tool. This is the first way you can create the interface, or you can deselect. Let me show you. Okay. This was the nano. There is a tool for convert to molecules. You can see when you click the convert, now this crystal is converting into the molecular structure. and the second one was the MOS2. So now I'll be do it the same. Now this is also a MOS2. So I'll be do it same. Go to the build option and interface builder and let it be same. Match it and click preview. So maybe okay. So ranges you have to change it. You have to take one by one and do the match and click preview. And you can see some interface structure are shown like this. So if we have some particular type of material, so we'll go with the that will be a give a more information about our structure. So it is a we take the arbitrary structure. No? So maybe interface are not making perfect, but this is the way how can you make the interface structure using this tool. So I have let me take in the another material. So maybe that time work. Can take the silicon. Yes. So this is the interface builder where you can make your structure, interface structure using the for the different type of material. So we have also a tool which is a CAD to atomic, in which someone don't have the information about the molecular structure. So they wanted to create structure. So they can directly do the they can use make the structure like that. Like we have take this tree structure. So I'll take it again. So after that, you can using like CAD instruction, you can make the structure. Now this is your interface is ready. Now you can select the what type of. Now you can after that you can select the what type of material you want to take. So you have to double click on it, and yes, sir. Deep Shekhar sir, you're asking something. Okay. So from there, let me show you. Can change the orientation and it's not working. So when you click on right and click set, and after that you can give the orientation of the material, and you can select the material as well. Like we wanted to create, like we had selected this type of material. We'll only go with the two materials. So let me delete one. And we had right click on it and click set. And you can change the orientation from here. Or if your project is into the offline library, into the somewhere into the file directory, you can also take from there. So like I will select here, you can change the length, and I'll select it okay. And for this another model, I will select the another atom, add another molecule. So I'll take it the okay, and I'll click the calculate. So you can see, I'll just click on fill. I'll be click one by one. Date sample. So this is also a method. So for the structure, You have to change their orientation. You have to know about the orientation values for the better understanding of the interface. So basically, these are the tools for the making the structure and interface structure as well. So you can select this one. Let me click one. Click and preview. So direction is incorrect. That means that so now let me default here. It will click preview and it will be same as well. So someone wanted to not, they wanted to change the orientation of their structure. So they can select the atoms and you can select these atoms, whole atoms, and there is a tool for changing the rotation. So this is a rotation tool in which they can change the rotation as well. Like I wanted to change the rotation to the 90 degrees. So first they have to strip the atoms. Okay. So now that method, they can change their view of the direction like this. Now after that, they can unselect it and do it, select it and do the center. And okay, now this comes to the center part. Now by that method, they can perform the many more things, make the interface structure as well. Okay. So if someone have another particular query regarding this devices, so they can ask me please. Then after I will be go with the another part of the video. Just I wanted to give some basic information about the tools and things. Let the I will be I will be let to performing this calculation. After the lunch, after the break, will be discuss about the another part of this video. Okay. So if have someone have particular question, they can please ask me. There will be discussed for the molecular dynamics for your with you. After the break, I'll will be meet up again from the 2 p.m. So everyone, to thank to all of you to attending this session. So we will meet again on 2 p.m. So so kindly request to all of you, whatever I done this simulation and making the structure and perform them to do by their own self to get the familiar with the software.
Excuse me.
Yeah. So,
Some of these options are not available when I'm trying to do it, like or converting the atoms into some different elements. And orientation also, if I'm rotating them, then I'm not able to select the atoms. If I'm selecting the atoms, I'm not able to rotate them. So
No
I don't
problem.
know what is going
Maybe
on.
maybe there is some things you are missing, so we'll be discuss on it. You can after that I'll be connect with me and I'll be see that what the things you are getting faced. So it will be more
Mhm.
better.
Is it like if we select, then only they will the options will be available, or when the file is open, then only these options are
Like you
by.
wanted to see, like I had selected this atom, okay,
Yes.
and I wanted to change orientation.
So
So
your screen, they are all are available to you. But when I'm trying to do in this my device studio in my
okay,
laptop, then I'm not getting these options available.
which version you are
They are
using, sir?
the same which
Device.
you have given us.
Okay, maybe I think the 22 version also available there. So maybe the
Yeah,
thing
no, but
which
it's only.
so you can share your screen. You can send me a picture of your desktop on WhatsApp. I'll let me see what things are happening.
Okay. Can I do right now or after lunch? Means after
So
1 hour
you
break.
can send me right now. Okay, no problem. And I'll be connect with you all of you after the break. Will be
Mhm.
all of you to 2 p.m. So thank you all of you for attending this session. So you can leave now.
Oh,
Yeah.
okay, okay,
You
fine.
can share me. Shivpari sir.
Share,
Yeah,
share
Gautam sir.
right now.
Your
Okay.
dashboard, which we are not getting, which you are not getting the tools. Okay.
Like how to share in WhatsApp.
You can take the picture, no, and share me. You can take
Okay,
the
okay,
photo,
okay, okay, fine, fine, fine.
screenshot of it. Okay.
Okay, okay, fine.
So thank you to all of you. We'll meet again on 2 p.m. Like 2 to 4 minutes. Okay. So for this 2 days training program, uh, last 2 hours will be the end of this webinar. So I hope you get have the mutual understanding about our software, which we have provided to you. And I hope that you get the understanding about the software and will try to do your research into that particular uh, so into the particular research field. And if you get any type of issue or something to using the software, you can, without any hesitate, you can all of you, uh, we are available to connect with you. So in this next video, I will be go with the two probe device, and I will try to calculate the DFT and EGF calculation using the for that particular two probe device. You can also create up to 6 probe devices using that our software. So let the come another person, then after we'll start it. Kindly wait. So maybe I think I should start it. The next session I will be created in this. If someone wanted to do with hands-on practice, they can also use this. They can perform their by their own side. I'll be create a two probe device using aluminum or a gold alkyl device. So I'm going to share my screen. Yes. So we am visible right now. So let me start my device studio. Can let me first show that structure we are done right that time. It is not the structure. So I'm looking for They not completed yet. I'll go to started the new to creating a two probe devices using this molecular builder of user interface. So I'm going to start right now. If someone wanted to do hands-on by their own side, they can perform it. So first we have to take the gold atom. So you can also take from the online library, or you can take the offline library as well. So we have to go into the import, import local, and 3D materials, and to the conductor. And after that, you have to go into the pure metal. You have to search for the copper aurum. That will be your yes. Okay. So now this is the gold crystal. So if you wanted to see the since this is a single crystal is there, you can see this is the total lattice area, total number of atoms, and its chemical formula. So now after that, you have to make this crystal into some specific type of crystal. Like I'll be go to the build option, and there is a tool for redefined crystal. So I'll be go with the redefined crystal, and you can see here is the face centered structure. So I'll be take the face centered. I click here, and you can see, and I will click the preview option. You can see when I click the preview option, it is a face-centric type of gold structure. And you can click on build. You can also go with the body centric, and you can click preview. You can see this is the body centric centered structure of gold. We have to go with the face centered, so we'll go with the preview. And now we'll go. Now this is the face centered structure of gold atom. So now after that, we have to go again this build option, and you have to do the redefined crystal again, and then you have to put some values, like I will put 2, and will be 2 as well, and 4. And click preview. You can see when I click the preview, some atoms are getting extended and in the particular direction. So after that, you have to click on build option. Now, okay. So then we have to, now this is your material. It's having the total 64 atoms, and its lattice area this, and their vector points are this. And now after that, we have to delete some redundant atom. So to removing the redundant atom, you have to select this. I'll be selected. So if someone are there, doing some practice by themselves, so you can see it very carefully. So you have to double click on it and select this upper atom, and delete it. There is a tool. You can see delete atom. I click here and atoms are deleted. Now we have to come into the another view. Like I'll be go with the XY view, and you have to remove the another redundant atom, this one, into this. And after that, we have to do the 3D viewer, click on 3D viewer, and after we have to remove this atom bit, but you have to unselect this atom as well. So that's you have to with control, you can unselect it, and using this delete atom, you can select it. So you can see my all redundant atom which did not I have to use. So I delete all of them. You can see like this. Now the next thing, so we have to generate some vacuum into this structure. So we'll go with there is a tool I wanted to show you, convert to crystal option. So you can go with this convert to crystal option, and you have to put some values to making the vacuum into this structure. So like I will put 18, and here 18 again. And you can see, I'll click on build option, and you can see the vacuum is created here. After that, I'll be do center along A and then center along B. Now your structure into the, you can see here, there's a lot of vacuums are created in this structure, and they are high, and this molecular structure into the center it comes. So now, after this, so we need to do a mirror atom. I need to the same atom. If someone wanted to create a same atom using the tool, so they have to select the atoms like this. They have to select with the right click, and you can see there is a tool which called you can see mirror. This mirror atom. When you click the mirror atom, and you can see XY view. I'll be select the XY view. And after that, I have to put some values. After that, I have to just select the XY view. You take the value of the maybe I have to put some value like 6.7. And I will click on apply. You can see when I click apply, I'll get the whole value and a mirror atom, mirror molecule of this structure. So someone is if are doing this, so they can also perform like this. So now we have to need some vacuum into the this Z direction as well. So I will go with the redefine convert to crystal option, and you can see I'll put some values here. Like I'll put it the 40 and click build. Now both molecule structure comes into the same vacuum, same space. Now we need to I have a, so I'll have to save, I already saved some atom for the middle part. So you can go into the file. If someone needs to that molecule, they can ask me to get the molecule as well. So I'll be import that material. I already saved that particular material. Okay. So this alkaline. Now we have to put this molecular structure into that between these two devices, two molecular structures. So we have to simply do the copy. And have to simply do the copy. Select like that. Click Control C, or you can do with and go into that structure and do the Control V. You can see now this structure comes over here. Now after that, you have to select this material structure like this, and into the center. You have to do into the center. Now you can see now your molecular structure is ready right now. So basically, this is the structure you have created by yourself, and you can see all these properties are there. Their number of atoms, there are 26 atoms are there, and their chemical formula is also ready. So now that this is the molecular structure. So now we have to make this is the two probe structure. Now we have to make this structure into that device part. So for device, as you know, go to the build option and convert to device option. You can click here. Here. So for making the device, I have to simply select the electrodes. Like I selected the left and right electrode, and their existing electrodes comes here. You can also, according to your convenience, you can change by yourself. And click preview option. You can see their electrodes are generated here. Now, after that, you have to click on build option. Now you can see your device, your two probe device is ready now. This is the basically AU alkaline based material. And now someone said that we wanted to add some more element into this between this center part of the device. So there is a tool for simulator, and you have to go on Nanodcal. And there is a for material part we use the we use the redefined stuff, but for device part we use this add to buffer option, in which we will put some values. You can see, click on add buffer option, and we want it to expand into the left electrode, left side. So you can see when I click on the left, the atom thickness is getting increased. For right as well as we can do it, and we can click build. So you can see now the number of atoms are increased into the center part. Okay, so you can see the chemical formula is also changed, and the number of atoms is also changed. So now after that, if someone wanted to do the calculation of SCF calculation, SCF NEGF calculation, they can also do by their own self. But in this video, in this session, I will be trying to make this structure into the transistor. So basically, we are not discussing about the transistor. So you can see, you can go with the simulator, Nanodcal, and there is a transistor tool. Okay. In the transistor tool, you can see when you select the transistor, there is things are coming here like gate region, IV curve, basic settings, contour integrals, and electrodes, and pressure control, and basic set, and spin type. All of things, whatever you put it into the SCF calculation are coming here. But the IV curve and the gate options is newly coming. So for this device, we wanted to make a transistor for this device. So for making the transistor, you have to put their dielectric permittivity value. Like there is a region type, dielectric and channel, and permittivity and thickness. So I will take the default permittivity. In the thickness part, you can put the some values, and you can put some value, like you can put 4 or something 5. You can see when you click on the 4, the thickness region is stand here like this. And you can change the, if someone wanted to uh, take the gate voltage of front gate type, you can select either top or bottom, or either you select the front and back type of electrode. So now we'll have to increase this. So maybe it will be gone. You can increase like bit voltage. We need to 0.4, 0.5 something. You wanted to bias voltage, you can take the 0.1. Like I'll take the 0.1 to 0.2 from the bias voltage. And after that, you will, for the IV curve, you have to put the K point samplings, their basic setting values, like LDA, what type of exchange collision you wanted to do the calculation. And to the K point sampling, you can put the values. And into the contour integral, you can put values as well, according to the TFT. So let the all values, you can take the default as well. And in electrode value, you can, if in this transistor, you can also perform the spin type calculation. So after that, when all values are getting put by yourself, you have to do only generate files. So you can see when I click the generate files, there are a lot of folders are created here, like device, left electrode, right electrode, and VD for no gate from VD 0.1 to 0.5. Then like here you can see 0.1 is VD is constant up to when gate voltage is gone to the 0.5 voltage, and then after 0.2 to 2 further gate voltage goes for the 0.5 voltage. So now that method you can create your transistor. Now this calculation for this device, the transistor inputs are created here like this. You can see here. Now after that, you have to run all the SCF input file. So first you have to run the electrode part. So I'll be click on run for electrode part. Then you have to run the right electrodes. Then after you have to run the device. After selecting the all calculations, all 3 devices calculation, left, right, left, and device, then you have to come with this VD 0.1, in which you have to run the first SCF input file. So you can come with this, let me see this. Okay, we selected the 0.1. Then you have to run the first SCF.input file. After that, you have to run the IV curve. Sorry, for this, we miss it here. So you run it here like this. After this, run it this IV curve. Basically, this point, this particular values are come for the single value, single input value. Then after you have to run this IV. or come with this VD 0.1 to 0 and gate voltage is 0.2. Run the SCF as well. Then after IV curve, then after you have to do the same for all of them. If someone is doing by their own side, please ask me if there is stuff to doing the simulation. You have to run all the calculations, all the input files. One by one. Now that method, you can conclude the things. So now you can see the all calculations are. First, you have to run the SCF dot input file. And now you can see all calculation are in the queue form. When one is getting completed, now you can see your left electrode is completed. Input is completed here. It takes the about to less time. So it takes about to 1 minute 43 seconds for the left electrode. Then after when it's completed, then right electrode SCF input file is started running. So that method they can do the simulation. Okay. Since you can see, all of you see that there's a lot of calculations are happening there. So it can take the time for to completing the whole simulation. So I wanted to show you after the closing this structure, I wanted to show you. I already do this. You can see right electrode is also completed the structure. And after that, device SCF input file is running right now. So maybe it can take a lot of times according to the system. If you have a better HPC, then it cannot take the much time. It will be take about to half an hour or something, half hour or 45 minutes something. So completing all of the structure. So now I have done this calculation past. So I wanted to show the structure, the another project of the same project which I done it past. So because wanted to show the how to analyze the result of the transistor. So let me show you. So basically this structure is the same as we are done. We are doing the simulation. So you can see I completed the structure right there. This is the same structure in which you can see all the calculations are I had completed. Okay, the all calculation are getting like this. In which you can uh, find a particular type of analysis as well. So now I wanted to plot of the IDBD characteristics for this transistor device. So you have to come on simulator, Nanodcal, and there is a transistor plot. Okay. Now we have to locate the file directory where you are doing this project. So transistor and locate that project file directory and select that folder. Now you can see this is the IV characteristics of output curves. I'll be expanded for 0.1 voltage to 0.1, 1 gate voltage, in which the VG current was 0.1 only. So let me show 0.2. Okay. So let me show you. These are the points we are getting. When you trace it now, we will get the exact curve. So this is the IV curve you can plot like this for the particular type of transistor. You have to run the all calculation. After the running the calculation, you have to do the transistor analysis, and by this you can see the IV characteristics of that device. So now this is the basic thing we are doing for how can you make the device, how can you make the two-probe device after the device making. You can create the device into the structure, a transistor. Then transistor, you can put all the necessary values like their SCF input parameters. And after that, you can plot the values into using the transistor plot tools. Okay. So maybe this thing you getting you could understand. I'm just trying to inform how this software can work. So now another thing, someone there is a research paper was there in which we have performed the simulation. So I'll be try to show you that project as well. So let me show you. If someone needs any question regarding the transistor, please they can ask me. Then after we will go to the further part of this session regarding the device, regarding the transistor or something. Okay, maybe there is no queries out there. So we'll go to the further of this session. So I'll have to someone asked. Yeah. Ravi Kumar sir, you are asking something, I think. Please ask me, then after we'll go to the further ahead. Can we apply pressure on the feature? The pressure part in the DFT calculation, or if there is these things are possible, there must be things we can do. But I do not have the idea about this pressure part. So we can also discuss with it the more information of your particular project or particular structure. So that will be a better. If you have any question regarding this transistor part, so please ask me any question. Okay, we have to go further again. So I'll showing you a simple molecular structure. How can you click on how can you create an armchair device of, I'll take the, first I'll have to take some material, then I will explain more of things about that armchair device. So let me show you. Yeah, ma'am. Sir, someone asking me a question. Okay, we wanted to go ahead. So let me take the material. I'll have to go import and import online. You can know all of them. You can take the material from online library as well. So I'll have to take the material. I will take the WT2 material. The which this is the research paper project, which is journal project, which we turning using the Nanodcal software. So I wanted to show you all of you. So basically, this is the material having the P3M1 type of space group, and we have to add it. Now, after that, so I'll remove it. Like this is also like previously we are doing the structure that we are creating using the MOS2 for MOS2 structure. But basically that was not the armchair, but this structure will be armchair type of device. So you can see I'll here T4W2 from the online library, and I'll do the center. After that, you can change the orientation and their axis as well. So changing it, we have to do this. Like I'll be go with this, and the YZ, I'll change it, and I'll be change the orientation axis as well. So I'll be go with this type of this structure. So first we need to expand it into the some different direction. So go to the build, and you can go with the redefine crystal, and you can select. You have to take the some value. If someone wanted to do try to make this structure, please go ahead. And if getting any problem, they can ask me as well. So now you can see preview. I click the preview, and I click the build. And after this, now this we will try to perform this structure on this material, on this type of orientation of material. And you can go again with build, and redefine crystal, and you can take the 3, and it will be 8, and you can click on preview. Now you can see this is your material. Now this is the material. So after that, now we also in this material we also try to do the doping of gallium atom into this particular structure. So please see the carefully. I'll be try to. I have to remove some atom as well. So I have to remove this. You can select this atom and delete atom. You can see. Now I'll be try to add some atom of gallium to change its property of this material. So by that material, you can go with this, like this. Using this, you have to do the replace atom using this tool, and you can select the gallium like this. I selected, and you can see this is the material. This is basically a armchair device, and in which I create some defect and use some doping as well. After that, now as well as now your material is ready. After that, you can perform the. Okay, 1 second. Now you can now after that, as you all know, our material is ready. Now we have to make this structure into the device. So for making the device, build, convert to device. You can also perform the some molecular structure using the, if you wanted to do some optical properties calculation, on the DFT calculation, you can also do the all of calculation of this particular material. But we will try to do the next part for the NEGF calculation using the Nanodcal, and then simulator, build option, and you can see convert to device or. So you can see when we are selected, and you can see we'll select the top and the bottom electrodes. So maybe you can see. Basically, this is the direction having the different view. So you can see here, but exactly the direction that come like this. So that's why I selected the top and bottom electrodes. So you can see their default values are also selected here of thickness. If you wanted to change according to your convenience, like their thickness, you did not want it to take this thickness, you can change it. Okay. So okay. So now you can click on build option. Now your device is ready. After that, you can do the TFT and EGF calculation for this material, for this device as well. Like you can go with the simulator, the Nanodcal, and same as you can put all the necessary value you wanted to calculate. So the first thing, the first we have to create their SCF input. So for the making the SCF input, you have to put some value like this. Let me show you. Simulator, Nanodcal, SCF calculation. And after that, you can put some values like I will put, you can take the value default as well. So no worry, no problem. It will be come for the research part. So let me show you. Contour integral, electrode, equation, and basic sets values, pin type values, as well as whatever you wanted to give of the DFT. So you can put all the values. After that, you can same as well as you will generate the SCF input for device, electrode, and some. And then after you run it all of them, and then just do the analysis using like go to the Nanodcal analysis and select the analysis like photo current, thermoelectric current, conductance, potential, feedback, AC, then all of the things you can select it according to your convenience. Okay. So now after that you can run of them and conclude your question. This is the basically armchair device I wanted to explore you. that it can be possible into that user interface. So maybe you get the idea about the project of this particular structure. So, if someone try to do the calculation of this structure, they can, if they get any issue of to making the structure, they can please ask me. Anyone? Basically, my main agenda was to, for this webinar is to getting familiar with all of the tools of how can you use these tools in your particular type of project or research paper. So basically, I wanted to explore the more and more tools to having that can comes to use of you. So you can calculate all of things. Now let me show you. I also do the calculation of this material. So let me show you. So this was the project. This is exactly structure. It is not this one. It is the structure. We had calculated. Now you can see if we wanted to see into that particular page, it was the structure. And it was calculated the different things, like I calculated the transmission. You can see this is the transmission input. Wanted to see into the some specific ranges. You can go with it. This. So can you plot the Raman and the fabric known to Raman? Raman is possible, sir, but at starting for you have to. I have to see your materials of what your project as well. So Raman is the possible if you have some specific type of structure or constant substance. And you can see here, I calculated the charge, conductance, total density of its electron density. And let me show you. This is the, you can see, this is the total electron density of this project. This is the 3D view. I wanted to see into the another view option. And you can go with the 2D model as well. You can see this is the total electron density of for this particular material. And you can see this structure like this. We did not use any type of spin behavior. So there is no spin issues like this. And along the average along Y direction, X direction, Z direction, we can select it like this. You can see the stereoscope display of this project. Into the X direction, you can see. Into the 1D graph, you can see this is the 1D graph of this material, this device, which we have created here. And you can also see into that, we can see this data into, I just select 50. And between the 35, now like that method, you can see the data. You can, after that, you can perform the calculation as well, whatever you wanted to do using this. After that, you can see I calculated the effective potential. And I open it. can see this is the effective potential of this graph. You can see this is the effective potential of this device. You can see 2D view, and you can also explore it according to your convenience. You can also export your data and image as well. So to the PNG form it will become. So by this type of thing, you can get your data. Now you can see 1D how we can so we have a lot of tools up there for making the device of, like I created this device, 2 probe devices I created in which I take the gold atoms and alkanol oil. So that method is whatever type of structure your will be there. You can create up to any type of structure like yeah. So first we have to make the material of the structure. After that you can make the simply use the convert to device option. Then you can create build interface type structure like I was showing you. Let me like you can see this is the effective potential. So there is a tool build and CAD to atomic. Here is a CAD to atomic tool where you can choose your material. Like you can choose the material as a box type, and you can do this type of and now after that you have to right click on it particular set, and you can choose the particular type of material you wanted to take and into the same of all of them. Then after build it, then it will come to the more than 2 atoms, more than 2 materials structure. So I was into the effective potential. So you can see you have to go into the 1D graph, and on the 1D graph you can see this is the 1D graph are coming here. So we have provided you can perform if you have getting successfully install the software, right? So you can perform the try to make the structure of your what type of molecular, what type of composition you wanted to do. So and then try to make the structure. If you not get, if you're facing some issue to making the structure, then contact with me. I'll be try to help you to make the structure. If that method the yes. So now we have also calculate the seebeck coefficient of this device. So you can see this is the seebeck coefficient. You can see for the seebeck spin and charge coefficient as well. You can see for the chemical potential energy, which is two graphs are there, blue and red, which is a spin up and spin down type of graphs. So you can also change the color as well according to your convenience. Like you can choose the yellow. And so this is the basic thing you can do using the this. Okay. So you can select the, let me change. Okay. So you can also see the values into some specific ranges. And after that, like you wanted to see the data for the specific temperature ranges, they can select it. They can unselect it, and like this is for the 20 Kelvin, and for 40 Kelvin, for 60, for 80, and 100 Kelvin as well. When we plot the band structure graph, no, so there will be a conduction and valence band are given. So either you can go with the extract the mat file or band structure, you can get the data from there, or you can also do the simple graph calculation, where you have to graph and you have to put on the cursor on the particular graph that will be show you the that value or the particular region. So that method you can get your conduction and valence band. Like let me show now. Let me show a band structure values. I'll be show you if you have done when you type when you extract the data into the MATLAB and load the band structure.mat file, and you have to type simply data. Okay. And after the typing data, all the information about the band structure, it will be come into the dashboard. And after that, you have to type data dot top of valence band. So it will be give to your valence band and value, and there will be a conduction band value as well. Bottom conduction band value. You have to type data dot bottom conduction. So it will be give you a conduction value as well. For band gap value, you have to type data dot band gap. It will be give you that value. In the description form, you will get all information about the, that band gap value. So if you wanted to see, let me, I done it right last time. Let me show you. You have to open a MATLAB. So things. I have to also show you the some MATLAB for calculation for this device, for particular device. So let me open it. MATLAB file. So you can see I calculate a lot of calculation for this device, like transmission and effective potential, total energy, scattering point. These are the calculation for the device part. So you can see this is the density of state for this material. You can see the density of state, but there is a lot of atoms are there. So you can see data for the particular atom as well. So you can select the particular atom and see the data for the particular as well. So because there is a lot of atoms are there. You can So you have to locate that file directly. Like we are doing some project last time. You have to open this project file. that. Okay, now this was the project we are done. So for band structure.net, you have to type data, and you can see these are the values. You have to type data dot for I let you come, sir, Prasanth Kumar sir and Ravi sir. Let me first. You can see this is the band energies, and this is the top valence band. You can copy this and type here and click enter. You can see this is the. You can also see from here. This is the top valence band value, and for bottom of conductance band, you can see like this, or you can copy this data, this text, Control C, and type data dot bottom of conductance band, and click enter. This is your conduction band value. For band gap value, so you can type data conduction. So this is your band gap value. So sometime you can also ask me, what is the Fermi energy of this? How can you calculate the Fermi energy? So for Fermi energy, you have to upload this. You have to load this Nanodcal object mat file, and you have to type object dot Hamiltonian. And click enter, and you can see this is your Fermi energy of that project we are doing last time. This is your Fermi energy. By that method, you can see the Fermi energy of your calculation. And you got it. Then yeah, if you have some for IV, if you have some specific materials are there, you can perform the DFT, and after that you can make the IV curve, and you can get the data. From XRD data, I'll have to discuss with my developers for the XRD things. Yeah. So what is the physical interpretation of the device? Like by making device. For electrode, the electrode will be like, okay. For electrode part, so like when you are creating the structure, so there will be a material, and when like this is the material, and your material should be maybe your you can select the electrode like left or right, sorry, top or bottom, front or back, or back or front or top or bottom or left to right atom. So by that convenience, you have to make your electrode like whatever you wanted to, like we have, like you can this is the structure now. So you can also deselect of this all you wanted to change this electrode into the copper one. So you can select this whole atom and replace this atom with the copper or gold something. So that time it will be converted into some specific type of electrode. So this is the also way, or you can when you are creating the molecular structure. So previously we have to assume that I have to make this area into the electrode. So by that method, that convenience you have to make the material composition. Okay. For absorption, we have uploaded a video. I'll show you. I uploaded a video on YouTube. You can go and watch for absorption and absorption energy and formation energy as well. So you can perform the calculation on your site. You can see there's the absorption energy. So I'll done it. So you can watch this video and get the information about the absorption molecule surface. Okay. I also uploaded some videos on formation energy. So you can also watch that video as well. So now I have to come that on that device which we have calculated here. So let me come into that file directory. I have to select that and after this, so now these are the calculation I completed. So now someone asking for the charge. So for the charge, maybe I completed this. For total energy, like we come with the transmission. So we have to load it and type data. And you can see these are the things have coming for this data. Can also see the total energy density value, electron density. So type data and you can see this is the total electron density. And you can type the data dot description for the more information about the electron density for this particular material. So to copy this, you can type it yourself. And you can see the all information you had get it for that stuff, what you are doing here. For that material. So at the same manner, you can go with the Seebeck coefficient, type data, and you can see the all information about, like you can see these are the chemical potential energy and the temperature. These are the points which plotted into that graph. Type data dot description. And these are the things are coming for that your project, that your particular material. So like, okay, so you can also do the for the conductance current and type data. This is your conductance value, and you can see now for the value of conductance, this is the DC conductance. So you have to type data dot conductance, and you can see this is your conductance value. It comes for that particular this material. And for charge, you have to load the charge and type data, and you can see these are the things are coming for the charge. So type data dot description, and you can see the things are given here like this. So by that method, you can go calculate the result into the MATLAB and get the information about your project as well. If someone have question, please ask me. Then after we go to the further.
Sir, suppose for our research, if we require to analyze the molecular configuration like XRD and other things of the material, then how we can proceed? Like then after we will go for specific properties like thermoluminescence and other things.
Yeah, sir. So for thermoelectric properties, we have to calculate that particular type of parameters. For XRD, I did not have the currently idea, but for XRD, there is a tool, no, currently not available, but okay, 1 second. Okay, so you can see there is a XRD plot graph tools is there, but when you have some specific data, you can import it and see the result as well. Okay.
Okay.
Yeah, this is the XRD tool are also there, so that time it may be work for you. One more device at top and down. No, it is not necessary. Either you wanted to make the same type of materials, and either you have some specific type of, you can change the materials electrode as well, according to your convenience. Some people are also working on the having the both have different type of electrode, so it's not necessary. Anything about the how to rebuild, redefine the 3D.
So can we able to import XRD data?
Yeah, actually currently I'm not explored much more, but I think there is a availability because XRD tools are given in this. If you have some particular things, then discuss with me. After that, I'll be sure about give us complete information about that XRD all things. Okay. Let me see. There is some. Okay. So maybe I did not use right now. No. So I'll be show you some tutorials I have already I'll be provide you tools who wanted to do the XRD things. So, but most of the peoples are more prefer for the origin or some expert tool for to do the analysis of the XRD, right? So that's why I did not use at that time for that XRD characterization. What is the price of the software? So the price of the software have the many type of policies are there. Basically, Nanodcal and this Rescu, which with the device studio interface comes about to about 7 lakh, about to 7 lakh something for a perpetual license. And if you take the into the single, then it will be have the some another policies are there. So for more information, after that we can discuss it. So, let me show one more application. So after that, we'll do. So basically, there are a lot of using this Nanodcal. There's a lot of applications are there. If someone are working on the spin type devices, they can also go with it. It can have the semiconductor devices application, molecular electronics. They can work graphene and other 1D and 2D type of materials. If someone have the area of material science and the chemical science, they can work. There's a lot of battery and energy storage type of applications are there. And there's transport type of application, heat transport, phonon transport are tools are there. So they can have a lot of applications are there in that software. The thing is, they have to do the more explore into this software that will get the more familiar. They'll be able to see the availability of our software. So let me show an example.
How we can get more familiar? Like one option is YouTube, and any other option we have
YouTube
for
and yeah, you can perform your particular type of project, no? Like and do the like make the structure and do the get familiar. Try to make particular type of research you wanted to do. So that will be help you to more able to. We have also a documentation page. So let me show you documentation page are there. If someone wanted to get the information theory of behind this DFT implementation, so they can go with this like Nano Academy and the Nano Academy. You can see here Nanodcal in which they can select the documentation and tutorial Nanodcal, and you can see if someone wanted to get the information like what theory is implemented behind this. So they can come over like introduction DFT, Nanodcal, and GF, how implement the DFT into the Nanodcal. Then after there is the tutorials also are given for different type of. We also uploaded in the future and also uploaded a project into on the YouTube, so they can get familiar with this. And there are a lot of research paper also there, so they can go also with them, like the Google Scholar. Let me show you. Let me show in Nanodcal. For rescue, that will be same thing. You can see there's a lot of research paper. If someone wanted to do some specific type of thing, they can type Nanodcal plus. Someone wanted to do the calculation like graphene. They can select and click enter. You can see perfectly. There is a lot of research paper are published using the nanodical having for the graphene type material. They can explore it and take the parameters and do the on the device studio, perform the calculation. So that will be helpful for you to get the family. You can see the structures are making here, and their values are also given. What type of exchange correlation, what type of cells it use. So it's all about the things you can see. You can see this, it takes the 0.25 voltage to 0.54 voltage in the bias region, the voltage region. So now that method, they can get more exploration about this software. For rescue as well. Rescue basically a DFT calculator for the and having the. We have also a plus version also available. So if someone wanted to get more information about our software, they can visit this website. And, so they're all of things like what type of CD potential, numerical, like some things are not getting extracted from the data, so they can come here and type their problem and they can also get your result as well. No, currently we did not have the video on the piezoelectric.
Sir, my question is that, sir, we have CIE inbuilt in this software. CIE 1931.
Pseudo potential.
No. Commission of illuminescence means color measuring space is there.
Color measuring space.
CIE.
Exactly, I don't have idea about it currently, but I'll be discuss with it and I'll be take if it will be there available, I'll be provide you information about this.
Okay.
Okay. So you can see using the rescue, you can calculate this type of calculation like band structure, band unfolding calculation, Barry curvature, boundary condition, Poisson equation as well, and DFT. These all type of calculation you can do. You can do via using this software. You can also work on the linear function calculation and spin DFT. And also tutorials are available there. So they can perform the tutorial as well. In the YouTube, there is a lot of research. There is a lot of file we have provided to you. You can also get the try to lot of tutorials are there. They had provided, so you can download it and simulate them to get the familiar of it. Let me show you. You can see this will help you to do the get familiar of the software. You can see there is a lot of projects are there. You can perform these projects and try to find what type of things you wanted to do. So that will also work for you. So getting familiar of the software. Okay. If someone needs some specific type of this type of calculation or something, they can ask me. So maybe I'm trying to explore more of things about this tool. Maybe if someone have to some specific questions or regarding that, they can directly contact with us. And after that, like the CIE color diagram is possible into the set for software. After into the into the 1 or 2 minutes, my colleagues, my senior colleague will be take this meeting, and there will be another software out there that for which is for the color that question are asking with that I think Dr. Praveen sir.
Yes, sir.
So yeah, so they will be provided you about the one another software that is a set for software. So please please have the attention to take the meeting. So,
Thank you, sir.
Hello, can you hear me?
Yes.
Okay, perfect. So some people were asking about CI color diagrams. Okay, so myself, Anil Sharma, I would like to share something
Yes.
new related to CI color diagrams, electroluminance, photoluminance, solar cells, kind of applications. So I want to introduce about one of our another partner company that is called Fluxium. This is our another partner attending
Sir, your voice is
training from
breaking.
last. So that was your nano. Hello, can you? Am I audible? So basically, this SatFos is a Switzerland-based company which developed the software for solar cells and LEDs applications. These are scientific product. One is called SatFos. The SatFos is for LED applications, luminance, ELPL measurements, simulations basically, including perovskite, tandem, thin film, multi-junction solar cells in one-dimensionals. And this allows it for two-dimensional with module simulations for large area applications. This is one of the equipment for characterization of IB measurement, optical measurement. And this is angular dependent ELPL measurements, PHILOS. For degradation analysis, LITOS. And stability analysis of perovskite application, this LITOS light product is there. So this is multiple product. Each product description, you can also look into the different brochure, which is given on this website, fluxim.com. If you go to this SATFOS, this is one-dimensional solar cells, perovskite and LED application tool. I would like to demonstrate about this SATFOS. That is one-dimensional solar cell and LED with emission and optical property calculations, including electrical. So multiple product is also there from this company as well, which we are representing. I want to demonstrate the SATFOS. If someone interested in other application, then we can also organizing one complete training on this tool. So this is SATFOS. If you see here, it is another software. It is not dependent. It is not dependent on other product which you attended, Nanodcal and Rescu. Nanodcal and Rescu both are from different country, different company product. And this SATFOS, that is for different country and different company product. It is no relation with each others. Now, if you talk about the CI color diagram that you were looking for, these are the existing example which is given in our library. So since we have a shortage of time, so I want to demonstrate directly the example here. So if you look into this particular example of full OLED, there is a glass substrate is there. ITO is a top contact. Volt transport layer is there. Emission layer is there. Electron transport layer is there. And backside aluminum and there air. You can visualize the layer structure in the right side of this particular, whatever it is created. We can also create our own customized layer stack. And that layer stack can be added or deleted. The thickness can be changed. Any manipulation in the structure can be done. Right side, you can visualize the layer structure with their energy levels. The HOMO-LUMO band gap value can be visualized lower of the energy structures. So this is default given one structures. I want to simulate this particular structure, but if you want to go to check the different parameters, we have an optical refractive index parameter where we can define some NK data, some optical data which we have calculated from material simulations, some semiconducting property, charge, transport property, HOMO-LUMO, mobility, dielectric constant, doping type. This is our lecture tab for time being so that all the parameters we can visualize. So you can define your own excitons for the LEDs, some TADF, thermally activated delay fluorescence, low energy to high energy transfer rates, some quenchings, energy transfer parameter, exciton quenchings, some traps, SRX recombination, traps or trapped recombination. You can capture electron and holes traps, single energy, label traps and exponential, and density of state traps will also be there. So if you see here, this is multiple trap parameter for single energy, exponential density of state, Gaussian density of states. This is all as input parameter. Ion transport is also there. Ion transport where you can define some anion and cations. So anion and cation can be associated with that. Mobility, minimum mobility, maximum density can be specified with the recombinations parameters. So this is all about Langevin recombination, Auger recombination, bimolecular recombination, and simplified SRH recombination parameters, including the impact ionization is also there. You can define your impact ionization feature. That can also become possible. Now, if I run the simulation, the calculation will start here. and simulation is done, it will not take much time as DFT simulation take. If you want to see the emissive property, this is CIE color diagram, which you were asking that questions. So this is CIE color diagram. Emission angles, you can also vary it. If you want to see the other properties, some luminance, even some other electrical profile, Venn diagram. This is Venn diagram with HUMO-LUMO energy levels are also there. Some charge density plot, electrical field plots, some excitons, rates, mobility, potential, recombination, graph is also. If you want to see the spectrum, emission spectrum, this is for emission spectrum. Some spectral analysis is there. Some optoelectrical generated photon calculations. If you want to see the luminance, this is for luminance. Radiance property will be there, but I want to show in some other example. Let's take this full OLED. So ITO, empty data, alpha NPD, BLQ, TPBI, lithium fluoride, aluminum. This is one of the structure in this particular example. And if we run this with it, this is one of the radiance property. You can see the current efficiency, some luminance property, peak emission intensity on different graphs, including the emission spectrum on different temperatures. If temperature is vary, if you want to see the spectrum, normalized emission spectrum or white emission spectrums, that visualizations can also be done, including the device efficiency curve, quantum efficiency curve, and all current voltage. This is the current versus temperature curve, internal quantum efficiency graph, and many more things will be there. In this left side, you can find a lot of examples are given for different type of structures. Similarly, if you want somebody want to work on solar cell, I would like to show you one of the example for solar cell application. You can see. Let's take this one of the example where ITO, some whole transport interface layer, perovskite layer, interface layer, C60 and silver layer. This is one of the structure. You can see the right side layer structure, energy levels also. How it can be modeled, that we will organize one training on coming days, which I am sharing you the information about the coming training on this tool also. So simulation is done here. If you want to see the IV characteristics, this is IV characteristics for this particular solar cell with interface recombinations. So if any doping concentration is varying your IV characteristics, we can sweep and optimize. This software is very fast in running the calculations. It does not require high-end computational powers. Similarly, if you want to see the effect of traps with respect to concentration, you can see I am varying the concentration, then how the current voltage curve will be changing. Similarly, you can plot the fill factor value, open circuit voltage, maximum power currents, and some electrical characteristics. With variation of voltage, if you are changing the voltage value, then how the band gap is affecting, either with respect to voltage or if concentration is affecting, then will also be seen the visualizations. So you can define multiple layers, unlimited semiconducting layers can be drawn, including some texturing. I would like to take one of the another example. So this is someone already created. If you see this particular structure, this top ITO, SNO2, C60, perovskite, nickel oxide, interface, metal ITO, amorphous silicons, and so many layers are there. So one of the tandem perovskite silicon structure is there with different energy levels. Optical semiconducting property can be defined even if any parameter is unknown. If you have no idea about the thickness, no idea about the voltage, temperature, work function of any material, then sweeping and optimization is there. You can optimize the value, minimum and maximum value you can set, and then the software will suggest at what value you are getting the maximum efficiency. So this is one of the structure which I am going to run the calculation. The simulation is starting. That will show the calculation percentage here.
Thank you, sir.
So we are also organizing the hands-on training on this workshop, on this software specifically on 12th of this August. So if you are interested, you can also like register yourself so that we will provide some license. Restriction will be there. Around 50 license we will distribute for 1 week period. So our next scheduled hands-on training on solar cells and LEDs application using the software which I am demonstrating right now, which will cover up the perovskite solar cell, organic solar cell, thin film solar cell, tandem solar cell, quantum dot solar cell, perovskite LED, organic LED. So from scratch, we will show you how you can model such kind of things, what kind of different property you can also analyze by using that set for software. So this is upcoming training on 12th August. It is a 1-day program only. So if you are working specifically on micro level solar cells, different kind of solar cells and LEDs, then it will be very good opportunity for you where you will understand very good capability of the SatFOS tools. So you can see I started the calculation, which is simulation is running. It is showing the percentage. It will take hardly 5 minutes, 10-minute time. And now the calculation is stopped, is completed. If you see the band diagram at the interface region, I can maximize that particular region and I can see the band gap for multiple layer structures. You can see this is a band gap for perovskite and some interface regions. If the voltage is changing, then how the voltage affect your band diagrams. Similarly, if you want to see the interface SRH current value, so this is one of the IV curve. Power conversion efficiency can be plotted. This is power conversion efficiency. If you want to see the electrical parameters, the BOC value can be calculated. Current density value, fill factor, maximum power density, maximum power conversion efficiency for multi-junction devices. If you will multiply around 28%, you can get it. Similarly, all characteristics you can plot from this particular software. Recombination, Language recombination, SRH recombination, biomolecular recombinations. It is also one of our key software where people are working on it and they actively publishing the paper on this tool as well. So this is one of the another software where people can work on tandem solar cell, thin film solar cells, and some amorphous silicon solar cells applications as well. Even you can also calculate the quantum efficiency of solar cell. Hello. So this is one of the another example for solar cell EQE, where you can plot some quantum efficiency graph, some photocurrent plot. This is quantum efficiency and photocurrent, including power conversion efficiency. You can also plot with the absorption. So optical, electrical, and emissive properties calculations. For advanced quantum dot texturing, nanoparticle effect, we also have different, this is scattering type nanoparticle, where you can define some quantum dot or phosphorescent dye. Some emitter layer like down convergence can be defined and you can plot it. For AC analysis, so it can perform not only a DC calculation, DC, AC and transient simulations can be performed. If you see, this is one of the example, gold top electrode, organic material, calcium bottom electrode. For impedance related calculations, this is one of the another example where you can plot AC analysis, AC current, AC phase, conductance, impedance. Schottky analysis, Nyquist plot can be taken from here. Z and Z naught, real and imaginary part of impedance can be extracted. Simply either in the form of image, you can export your data, or in text format, the data can be exported very easily. So this is also one of the renowned software which is widely used in many of the global universities worldwide. So all for electrical, optical, emissive calculations for LED, solar cells, tandem, thin film, this software will be quite very useful. If we want to perform the transients also, so we have this transient solver, not only a drift diffusion solver, we have a steady state solver, transient solver, AC impedance solver, and intensity modulated photocurrent photovoltaic spectroscopy analysis. So different solvers are there, and accordingly, we can plot the characteristics. With respect to time, the calculations can be performed. Time steps calculations. So I invite all the persons, all the participants, you please register and come on 12th of August to attend the hands-on training on this particular software, which I assure you it will be very beneficial for your research. So from our side, thank you very much to all the participants. If you are interested, you can also unmute your mic and you can put up your queries so that we can.
So what is the cost of software?
Sorry, can you please repeat?
What is the cost of software? Cost.
Which software? This one or the Nanodcal one?
No, this one. This software. Thin film related.
Yeah,
what you have presented.
Yeah, for this set for software, cost is basically dependent on module. There are some 4 modules are there, and validity 1 year, 3 year, 5 year, 10 years. 1 year, 3 year, 5 year, 10 years.
Okay, if it is a thin film module, if I want, what is the cost for 1 year?
For thin film, only 2 module, optical calculation and electrical calculation. That will cost around 2.5 lakh plus GST. So approx 3 lakhs
for 1 year.
For 1 year. For 2 modules.
Okay.
Minimum 3 lakhs, yes.
Okay. Okay, sir.
It can perform unlimited semiconducting layer, transient simulation, interface will be there, swapping and optimization, multiple parameter at a time you can sweep and optimize, and many more recombination, state of art, mobility model, DCAC analysis, impedance characteristics, many advantage will be there in this particular tool as well. So any other participants have any query, you can unmute your mic. From our side, thank you very much for giving your time. And please keep in touch with us. Try to use the software. That license we already given for Nanodcal and Rescue for 2 months validity. So just explore as much as you can. And later this workshop also, we will be happy. If you have some doubts, some query, you can type. You can email us. You can call us. You can type your questions on the WhatsApp group as well. We will surely help you. And we have given the feedback link on the chat box. If you require e-certificate, within a week, you have to fill this form to get the e-certificate to attend these trainings. So if any participants have any query, you can unmute, you can type, and So from our side, thank you to all the participants. Please keep in touch with us. Try to explore the software as much as you can, the license which we have given. So software is already installed. The activation is already started. So activation is already started. The license will be valid till 25th of September. So thank you very much. I am now closing the session.
Thank you, sir.
Thank you. Thank you all.